Okay, so last time we had seen the drain characteristics or the output characteristics, where we had seen working or change in ID when VDS is changed for different values of VGS. Now we'll see the transfer characteristics or the characteristics between input and output. We'll call that input as VGS and output as ID. So what is the behavior of transfer characteristics, that is input versus output? ID is considered as output, and as usual in the previous also we had shown ID on the y-axis. Similarly we are showing ID on the y-axis, but VGS we are showing on the x-axis but on the second quadrant. Why? Because second quadrant, because VGS is negative, which is applied to this N channel field effect transistor. Okay, so what is the behavior if VGS is 0? If VGS is 0 and now this characteristics is for the fixed value of VDS. We are giving some fixed value of VDS and will be changing VGS and finding out what is the effect of change in VGS on ID. So the effect of VGS on ID will be plotting in this graph. So when there is no VGS, that means the depletion layer will be minimum. Whatever will be the depletion region, that will be just because of the VDS applied, and we have kept VDS constant and we are going to change VGS. As VGS is changed, initially VGS is 0, that means the depletion layer is minimum. When depletion layer is minimum, that means we are having the cross section area maximum. When cross section area is more, the total resistance is less, so more current flows. So that's why at 0 VGS you will find maximum ID current. This current is also called as IDSS. That means drain to source current when VGS or a gate is short circuited. So that's why it is named as IDSS. This is one of the specification which you will find on the specification sheet of a JFET. So at 0 VGS maximum current, as VGS goes on increasing in the negative direction, that is we are going to increase VGS. That means as VGS is increased, the depletion layer goes on increasing. As depletion layer increases, effective cross section area goes on decreasing, and that effective cross section area, as it goes on decreasing, the resistance goes on increasing. As resistance increases, according to the V is equal to IR, we have kept VDS as constant. As resistance increases, we will find ID current decreasing. So that's why you will see the ID current goes on decreasing, and at one point this current reaches to 0, and the point where this current reaches to 0, or the voltage at which, the VGS voltage at which the ID current reaches to 0, is called as VP, or pinch off voltage. VP is equal to pinch off voltage. At this moment or at this time, there is no current flowing because the cross section area totally has become 0. Why? Because the depletion layer is totally because of VGS, and that's why it is not depending on the current ID which is flowing between drain to source. That's why the depletion region reaches to 0 and there is no current flowing, and that's why at VP point your ID current becomes 0. So this is what the characteristics. You will find this characteristics is not linear. When that is not linear, that means there should be the expression for this, and the expression is given by Shockley's equation. Shockley gave an equation for the behavior of ID with respect to VGS. Shockley equation, which says ID is equal to IDSS. IDSS is the maximum current when gate is short circuited, into bracket 1 minus VGS, voltage applied between gate to source, divided by VP, pinch off voltage. Again VP is a fixed quantity which is given in the specification sheet, raised to square. So whenever this square comes, that does mean the relation is exponential type, or the relation is curved type. So that's why change in VGS changes ID, but it is not a linear. It is somewhat a type of a parabola. So this, remember this equation, ID is equal to IDSS into 1 minus VGS by Vp whole bracket square. This is called as a Shockley's equation.